Everyone, I'm Won-Lee. We have dealt with one population testing hypothesis problem, mean mu, proportion p, and variance sigma square for one population. But now we move to two independent populations problem. Test the hypothesis for the difference between two independent populations. We often encounter this kind of a problem for some purposes. So you have to understand this kind of a material very well, then you will understand the next statistical hypothesis problem. Okay, let's see what is this problem. Okay, testing hypothesis for the difference between two distinct groups, say independent populations. Two distinct independent population problem. This is a problem of investigating whether there is a difference in the means of variables being analyzed, such as between metropolitan area and versus non-metropolitan areas, men and women, or commercial banks and securities companies, that kind of two independent groups. We denote random variables representing population 1 and population 2 as x and y. Here x, population 1, and y for population 2. And their means are mu1, mu2. Okay, variance sigma 1 square, sigma 2 square. Okay, that is a set of two populations. It looks complicated, but it is as simple as when we deal with one population thing. Okay, in this case, the hypotheses are H0, mu1 equal to mu2, H1, mu1 is not equal to mu2. Of course, we need to obtain samples from population 1 and population 2, like x1, x2, xn1, y1, y2, yn2. And their sample means are x bar and y bar respectively. So no problem yet, right? But how to test this kind of hypothesis looks complicated, but it will be changed to this. H0 mu1 minus mu2 equal to 0 versus H1 mu1 is not equal to 0, right? Equivalent. Same thing. You may test for one-tailed hypothesis. This one is two-tailed, but one-tail means mu1 greater than equal to mu2. H1 is mu1 less than mu2. That kind of a hypothesis are possible, as we did in testing hypothesis with one population. Okay, same thing. Test statistic will be here, x bar minus y bar. This hypothesis mu1 minus mu2 is now new what? Parameter. So your test hypothesis, test statistic should be x bar minus y bar. And its distribution, we know the distribution of x bar minus y bar follows normal distribution, mu1 minus mu2, and variance sigma square divided by n1 plus sigma 2 square divided by n2, right? No problem yet. So now we standardize it. G equal to x bar minus y bar minus mu1 minus mu2 divided by what? What is this? Standard error of x bar minus y bar. It is a square root of variance. Then we get standardized normal variable G will follow normal distribution with mean 0, variance 1. And the rejection region for H0 will be like this. Same as the result from population 1, right? A little complicated thing here, but the logic is just the same as in one population problem. But now, a little difficult thing is we have to estimate sigma square. Sigma 1 square equal to sigma 2 square. Same thing, sigma square. And the variances are different case, two cases, as discussed in estimation section 4.7 and 4.8. We handled the cases, this kind of things. So let's see here, population 1, population 2, here mu1 sigma 1 square, mu2 sigma 2 square, and sample from population 1, sample from population 2. When x1 square equal to sigma 2 square, same thing, then we can denote it sigma square because they're same. So one parameter, sigma square. So we pulled the samples here, n1, from here, y1 up to yn2. We pulled it and estimate one sigma square. It is natural, right? How to get pooled estimator? It is from sample from population 1 and 1, sorry, oh boy, not that. xi minus x bar square plus yi minus y bar square. How many there? Here, n1. How many? n2. So what is the terminology of this one? Deviations. Deviation of x, deviation of y, squared, and the sum. And divided by what? Degrees of freedom. How many degrees of freedom here? n1 minus 1. How many? n2 minus 1. X and y are what? Independent, right? Independent groups. So n1 minus 1 plus n2 minus 1 is the degrees of freedom for this pooled estimator. So that pooled estimator, we will use pooled estimator here. Sigma 1 square, sigma 2 square equal, so sigma square. But, oh, this is error. Sigma times square root 1 over n1 plus 1 over n2, right? So we substitute SP pooled for sigma like this. Then standardized normal will become to be T, right? We studied it. So S pooled times square root 1 over n1 plus 1 over n2. That is what follows T distribution with degrees of freedom n1 plus n2 minus 2. So the rejection region now for H0 will be x bar minus y bar less than 0 minus T alpha over 2, and this standard error, or x bar minus y bar greater than 0 plus T alpha over 2, same thing. Actually, we will use this rejection region, okay? And how about this case? Sigma 1 square is not equal to sigma 2 square. Then sigma 1 square should be estimated from the samples, okay? This of x1. So I mean population 1, the samples from population 1 should be used for estimating sigma 1 square. And sigma 2 square will be estimated by the samples from population 2, y1, that is s1 square, s2 square. Okay, for this, s2 square is going to be yi minus y bar square, I1 to n2, from 1 to n2, divided by n2 minus 1, right? And this one, in this case, the degrees of freedom will be degrees of freedom for T alpha over 2, this value from what? Very, very complicated thing. I don't remember. I never remember. I never try to remember that kind of thing. Very, very complicated. Even degrees of freedom will be what? Will not be integer value. So we studied it, and we I think we don't try to know more about that because the computer will provide you the exact result calculation. Okay, so don't worry about that, and you know how it's going for this kind of problem, right? And the problem for differences among three or more distinct groups, we just did, we just explained for two independent population cases. But three or more distinct groups for it is problem of analysis of variance ANOVA in chapter 7. This topic is also important and I think very, very interesting subject. Okay, this is it today. Thank you. Bye.